Hey everyone, we are going to do some practice problems from Review Lab 1. If you're good with projectiles, you can just use the simulation to check these. You definitely don't have to watch this video, but if you're a little rusty or want to see how I typically solve these type of problems, let's go. So talk about choose your own adventure. Look at this. You get to write in anything you want, so you can't be wrong. Well, not true. You can be. Let's just go with, let's see, projectile launched horizontally. Ooh, that's important. Underline that. Let's go with the height of, you like 7 meters. Cool. And let's give it an initial velocity of 20 meters per second. Wow, this chord thing is annoying here. Let's see if we put that there. Better or worse? Better. Okay, so where should the target be placed to result in a bullseye? There's not one right way to do these problems. Lots of different ways to do it, but pretty much all of them involve splitting up the X and the Y. If you want to organize that information into a table where you have a column for the X stuff and a column for the Y stuff, you can do that where you list all the variables you know, what they're different for, X and Y. The most important thing here is that the acceleration in the Y direction is going to be negative 9.81 meters per second squared. That's little g. That happens everywhere on Earth. Constant. Hopefully you're familiar with that. And in the x direction, there's going to be no acceleration. Nothing is pushing it forwards, making it speed up, or backwards, making it slow down. So it has constant velocity in the x. The overall big pattern is, I don't know, some people call this like the range equation or something. I like to write it like this just to clarify my thinking. But delta x, change in x, that's going to be the range of the projectile, is equal to the horizontal velocity times the time that it's in the air. We can use a simple equation like this with no acceleration because there is no acceleration in the x direction. The tricky part is we got to find time here. We have to figure out how long it's in the air. And to do that, you have to look at the y direction using fancy kinematics and all that stuff over here. So in the y direction, an important thing to note is the initial velocity in the y direction is 0. And it's going to have, like I said, acceleration of negative g, assuming we have up is positive. We can use this equation here. I know that gives us the subscript of x. You can just switch that off for y if you like. But if we fill information into this equation, what we know about the y direction, the final coordinate we have for y is going to be 0 because it's hitting the ground. The initial coordinate is going to be 7 because it started from a height of 7. This middle term here is going to be 0 because the initial velocity in the y direction is 0. So 0 times t, doesn't matter, that whole term is 0, plus 1/2 acceleration in the y is negative 9.81 times t squared. So this whole thing simplifies down a little bit. So we've got negative 7 equals negative 4.905 t squared. So we can solve for t here. Calculated time, so 7 divided by 4.905. Take the square root of that. It looks like our time is 1.19 seconds. Hopefully that's close enough. Cool. Next, we take this time, plug it into the range equation over here. So our delta x is equal to the x velocity, which starts out at 20 meters per second and stays constant at 20 meters per second because nothing is speeding it up or slowing it down, times our time that it's in the air, 1.19 seconds. Check out the units there, meters per second times seconds. Those will cancel and give us meters, which is what we want because that is the range, the distance we're looking for. So 20 times 1.19. 23.8, they say. And let's hop over to the simulation and see if that is true. Okay, here we are in the simulation. To check our answer, all we have to do is set up our initial conditions. So launch height of 7 meters, launch velocity of 20 meters per second. If it's horizontal, set the angle to 0. And for dramatic effect, let's put our target there first to see if we actually get it right. That's always fun. 23.8. Possibly most importantly, choose a fun projectile. Car. And 5, 4, 3, 2, 1. 3 stars. Who's amazing? Physics is amazing, not us. Give the credit to physics. All right, here's another problem. This one is going to have a non-horizontal launch velocity, so it's a little bit trickier, so not too bad. Let's just go with a height of 15 meters. So projectile launch from a height of 15 meters at an angle of 57 degrees, just like the ketchup, and velocity of 3 meters per second. Where should we put the target? And check, we did choose a non-horizontal angle because it's more fun. Again, there's not one right way to go about this problem, but I think pretty much all of them are going to have to start with a little sketch of your launch angle. So if we have a speed of 3 meters per second, and that is at an angle of 57 degrees, something like this, you have an initial velocity in the y and an initial velocity in the x, assuming the, y, x positive in those directions like we usually do. So let's just call this Vy can be the initial velocity in y. Vx can be the initial velocity in x, which will actually be the same because there's no acceleration. And then we just got to do tricky kind of stuff. Vy is opposite, so that is going to be 3 times the sine of 57. And then this is going to be 3 times the cosine of 57. Make sure your calculator's in degree mode. If some of the big bad math people made you put it in radian mode, just tell them no. Physics is cooler. So 3 sine 57 looks like 2.52. We'll say good enough. Good enough for government work. 2.52 meters per second in y. And 3 cos 57, 1.63. And similar deal as before, you are going to use your information in the y direction to figure out the time that the projectile is in the air. And then all you have to do is multiply that time times your x velocity down here, because it's going at a constant velocity in the x direction. Nothing is speeding it up, nothing slowing it down. That's why we can use the just velocity in the x times the time. The y direction is a little messier because now it's quadratic equation world. Look like up here at the top of the paper, you can't see it, but we're going to be filling information into the second kinematic equation, and that's where we'll get all our quadratic-y kind of stuff. So for the y direction, our final position is going to be 0 because it hits the ground. Our initial position is going to be positive 15 because it starts at a height of 15. Now this next term is not going to be 0. The initial velocity is going to be 2.52 times t plus 1/2 times our acceleration in the y direction is negative 9.81 t squared. Clean this up just slightly. We have 0 equals 15 plus 2.52 t minus 4.905 t squared. And this is a quadratic equation. So that means we got to use either quadratic formula or good old-fashioned a quad in the calculator to get our solution. When we do that, negative 4.905 is going to be our A. Positive 2.52 is going to be B. Positive 15 is going to be C. And the whole thing's equal to 0. If you don't have a quad on your calculator, it's actually pretty easy to write your own version. I happen to have it here. Just look that up if you want. But A is negative 4.905. B is positive 2.52. C is 15. Cool. It even gives you that little fancy equation. And we get 2 solutions for T. Looks like T could be negative 1.51 or positive 2.02. And we're going to go with the positive version, 2.02 seconds is our time that it's in the air. And then we'll just finish it off with the range, dx times t. So our x velocity, the same the whole time. We found that in step 1, 1.63 meters per second times a time of 2.02 seconds. And our range looks like 3.29 meters. All right, let's see if that's correct. Over to the simulation. Launch height of 15 meters, launch angle of 57 degrees, and initial speed of 3 meters per second. This looks ridiculous. There's no way that physics is going to be right here. Is there? You know what they say. 1, 2, 3, 4, pumpkin. Wow. Let's zoom in for a little instant replay action. Pumpkin broken. Pieces on bullseye. Physics amazing. You smart. We did it. Nice work today, people. Let's take 5.